Okay, now we're going to be looking at the repeated measures t-test. So we've looked at a one-sample t-test. We've looked at an independent samples t-test that compared two independent groups from one another. Now we're going to look at the repeated measures t-test. That is just as it sounds. We're looking at the same subject, and we're looking at two scores for the subject. So a classic example is the pre and post test type of design. Let's look at them before an intervention and after an intervention and what kind of difference exists for them. Or if we put the same subject through two different conditions and we want to look at the different scores between them. The advantage of this design is it allows us to control for individual differences, which really causes a lot of the error right here, what we call error, what we call the differences we'd expect by chance. So one of the things here that we have is what's called a difference score. We're just going to take the subject's second score and subtract the first score from it. Now there's nothing magical about that. We could actually have their first score and subtract the second score, just as long as we do the same thing for every subject. That's what's important for that, for the difference score. So our T formula is the mean difference score for all the subjects divided by the standard error of the difference, or the difference we'd expect by chance between them. Here's our measure for that standard error of the difference. So it's just going to be the variance for the different scores divided by the sample size. And then this should look familiar to you. It looks like the computational formula for the sum of squares, and it's just the letter D, or the difference scores, are substituted for x's. Okay, so let's look through an example. Investigator wanted to see whether or not talking on a cell phone while driving really impacts driving performance. With 10 subjects, they drove on a course under two conditions, one while talking on a cell phone and another while listening to music. And we want to look at the number of errors that were recorded each time while they were driving. So here's what this data might look like. So here's the data that we'll work through. And so you see we've got every subject and that they went through each of the courses twice while listening to music, and this is the number of errors that Dave made while driving listening to music, and this is the number of errors that he made while talking on a cell phone, 5. And then here's his difference score, which was just the number of errors he made while talking on a cell phone minus the number of errors while listening to music. And so here's our set of different scores here, that was here. You'll see this can be an advantage in terms of controlling for the individual differences. For example, John looks like he's probably a bad driver pretty much no matter what. He makes a lot of errors even while he's just listening to music, and then even more while he's talking on a cell phone. Versus somebody like Katie doesn't make a lot of errors while she drives, even when she's talking on a cell phone. So we have their mean difference score. All this is simply all of these added up together to give us that mean difference score. So we've got 20 there. That adds up to 20 divided by the number of subjects that we have, which is 10. So it's 2.0 is our mean. So when we add it up, it adds up to 20 divided by our 10 subjects. We have 2.0 for the mean, and then the variance for this is 2.22. That's the variance for these different scores, and that's given to you in this problem. And it should be given to you in your homework problem as well. Okay, so let's go through our 4 steps, 4-step hypothesis testing process. And so our null hypothesis is that the mean difference score is going to equal 0. What does that mean? That means the null hypothesis is that when they're driving while listening to music and driving while talking on a cell phone, that they'll get similar error scores each time, right? That's what that would mean. Null hypothesis means no differences between groups. Here's our alternative hypothesis, and does not equal 0. So again, you remember, since it's equals and does not equal, that this is a two-tailed test. So our decision rule will set our alpha at our standard level of 0.05, and as we mentioned, it was two-tailed. Our sample size is 10. We have 10 subjects, so our degrees of freedom, right, it's going to be 10 minus 1 equals 9. So we're going to look up our cutoff scores in our T table in the back of the book. So our degrees of freedom are 9 here, and we go over proportion of two tails combined, 0.05, 2.262. 2.262 and negative 2.262. So when we do our calculations, reminder that this is the mean D divided by variance, which is divided by the sample size, and we get the square root of that. And so our mean D was 2.0. Do you remember? It added up to 20. We divided by 10 to give us 2.0. 2.22 was the variance for this group. Our sample size was 10. We get the square root of that. So we have 2.0, and then we've got 2.22 divided by 10, right, which will give us 0.22. Square root of that, 0.47. 2 divided by 0.47, 4.26 with rounding. And we look at that compared to our normal curve here. We're definitely in the critical region. What's our decision? To reject the null hypothesis. We reject the null, and we look at when we look at back at the data for this, then we can tell that for here there are significantly more errors while talking on a cell phone as compared to listening to music.